For decades, access to space was restricted by extreme financial barriers. In recent years, a massive drop in launch costs successfully dismantled those barriers. However, solving the economic problem of reaching orbit inadvertently created a severe physical threat to our ability to operate there. This economic barrier was rooted in physics, specifically the Tsiolkovsky rocket equation. The Tsiolkovsky rocket equation is a mathematical principle linking a rocket's velocity to its mass and exhaust speed. It dictates that to achieve orbital velocity, over 90% of a rocket's mass must consist of heavy propellant and fuel tanks, leaving less than 4% of the total mass for the actual payload. Because engineers had to maximize performance and minimize weight to squeeze any payload into that tiny margin, early rocket stages were entirely expendable. Discarding complex, multi-million-dollar hardware into the ocean after a single flight drove the price of space access to extreme highs. This chart plots launch cost per kilogram to low Earth orbit against launch dates. From 1970 to 2000, costs hovered in a stagnant cluster around $18,500 per kilogram. Starting in 2010, Falcon 9 and Falcon Heavy dragged the cost down to under $2,700 per kilogram. While reusability is often credited for this drop, the initial cost savings actually came from strict vertical integration and simplified design. Instead of developing complex, unique propulsion systems for every rocket stage, engineers utilized redundant architectures, like clustering 9 identical engines on a single vehicle. Shattering the Tsiolkovsky economic bottleneck rapidly transitioned low Earth orbit, or LEO, the region of space below an altitude of 2,000 kilometers, from a domain of extreme scarcity to a proliferated mass market. In 2018, the global aerospace industry launched roughly 300 payloads. Today, that rate has surged to over 1,500 payloads entering orbit every year. This volume is largely driven by commercial mega-constellations. Single corporations are now deploying networks that populate LEO with thousands of active satellite nodes simultaneously. The space sector has shifted away from a disposable, single-use model. It now operates as a continuous transportation system, closely resembling commercial aviation. With the extreme financial penalty of weight removed, engineers no longer have to build fragile, hyper-optimized spacecraft. They can design heavier, more robust satellites packed with redundant systems and deploy them in massive batches. This rapid deployment of hardware drastically outpaced existing space environmental guidelines. For years, mitigation norms were treated as suggestions rather than strict operational laws. The industry succeeded in making space access cheap and routine. By doing so, it overcongested the operational domain, creating a profound physical vulnerability. To understand the physical risk inside this newly congested environment, researchers rely on mathematical forecasting. Space policy analysts use stochastic source-sink evolutionary models, sometimes called particle-in-a-box models. These are mathematical frameworks that calculate population changes over time by tracking the rates at which objects enter and leave a defined space. These models track population vectors using 2 main variables: launch rates, acting as the sources feeding new objects into the box, and orbital decay, acting as the sinks pulling them out. But the system is complicated by a critical interaction variable: orbital collisions. Collisions introduce the central mathematical risk parameter, PXP. This represents the probability of runaway exponential debris growth. When LEO was historically sparse, the distance between objects was vast. The PX parameter remained incredibly low, making the orbital environment highly stable. In a proliferative LEO, the sheer density of hardware elevates the baseline collision probability. The mathematical threshold for an exponential cascade is much closer to reality. Objects in LEO travel at high orbital velocities of 7 to 8 kilometers per second. At these speeds, even a collision with a debris fragment smaller than 10 centimeters releases catastrophic kinetic energy, instantly generating thousands of new fragments.
The proliferated LEO environment is now mathematically primed for a chain reaction. It only requires a single major catalyst to ignite PX. The most severe catalyst for this reaction are direct ascent anti-satellite, or ASAT tests. These involve launching missiles from Earth's surface to intentionally destroy orbital targets, resulting in massive systemic debris injections. In 2021, a direct ascent ASAT missile intercepted and destroyed Cosmos 1408, a defunct Soviet military satellite weighing over 1,700 kilograms. This single event instantly injected a dense cloud of over 1,500 trackable fragments into orbit, alongside hundreds of thousands of microscopic pieces to monitoring. When a sudden injection of high-velocity debris intersects with densely packed commercial megaconstellations, the initial fragments strike active satellites, triggering secondary and tertiary collisions. Inside these stochastic models, this chain reaction registers as a vertical spike in the p-expep probability parameter. The debris population transitions into runaway growth. This cascading debris physically overlaps with critical inhabited zones. Fragments from Cosmos 1408 directly jeopardized the 400-kilometer altitude band, forcing the International Space Station to perform evasive maneuvers. Once the exponential cascade begins, the mathematics of the environment become irreversible. The rate of new debris generation drastically outpaces the rate of natural orbital decay. Without active intervention, stochastic modeling indicates that a single ASAT event in a proliferated LEO will mathematically trigger the Kessler syndrome, rendering the entire orbital shell physically inoperable. To counteract this rising probability of runaway debris, the aerospace sector is executing a strict systems engineering response. The new industry mandate is the Debris-Free Space Missions Framework, or DFSM. It targets a zero debris footprint for all governmental and commercial space actors by 2030. At the core of DFSM is post-mission disposal, or PMD. PMD dictates the controlled removal of a spacecraft at the end of its operational life. Under the new rules, these disposal mechanisms must be engineered into the satellite and proven before launch authorization is granted. Disposal systems for rocket stages and satellites must exceed 99% reliability. Furthermore, orbital lifetimes are strictly limited to under 5 years. Engineers allocate specific fuel to execute controlled reentries, deorbiting satellites below the 350-kilometer mark, where atmospheric drag rapidly pulls them down. Aerospace engineering is no longer solely focused on getting mass into orbit. It is now strictly governed by the physics of getting that mass back out. Even with an accelerated 5-year decay window, a decommissioned satellite remains a dangerous latent threat while it drifts. To neutralize dormant hardware, engineers implement a mandatory end-of-life protocol known as passivation. Passivation is the process of removing all stored energy from a spacecraft at its mission's end. The mechanics are straightforward. Residual fuel lines are vented, and batteries are permanently discharged. This ensures dead satellites cannot explode due to internal pressure or faults. During this entire decay phase, the satellite must maintain continuous trackability. Engineers mount passive reflectors and fiducial markers to the chassis, ensuring ground stations can uniquely identify and monitor the hardware until it burns up. When these strict disposal guidelines are paired with reusable launch vehicles, rockets that land themselves to be flown again, the industry closes the loop, creating a highly sustainable operational model. The economic triumph of cheap space access allowed us to populate low Earth orbit, but it mathematically pushed the environment to the brink of the Kessler syndrome. By enforcing rigorous life cycle engineering, the industry can stabilize those collision probabilities. The success of future orbital operations depends on absolute life cycle containment, engineering every mission for its eventual burnup before it ever leaves the drawing board.